Okay, let's go ahead and get started. I want to welcome you to the periodic table and periodicity lab. This is going to be a dry lab, so we won't have use for any chemicals, but we will need these little cards. You should see a plastic baggie on your laboratory desk, so just remove those. And you're going to need a fairly large working area. So find a space that you can arrange the cards in and not have as little as overlap as possible. So the first thing you're going to do is you're going to take the cards and you're going to arrange them, as Moseley did, by the way, in 1913, according to atomic number. So remember that Mendeleev had arranged the elements according to atomic mass before him, but there were discrepancies. There were problems with that system. So Moseley sets out in 1913 to try to correct those deficiencies. And so he places those atoms in order of increasing atomic number. So that's what I'm doing now. I'm just simply placing the atoms or the elements in the order of ascending atomic number. Okay? Again, I'll need quite a bit of room here because I'm just placing them from 1 to 18. I've got the first 18 atoms or elements here, and I'm just placing them in order from left to right, from low to high, in ascending order, just like that. Okay? If I need a little bit, I can stagger this if I need to, but as much as I can, I'd like to have these just go left to right. Here's 14, that's silicon with 14 electrons, phosphorus with 15, aluminum goes here with 13, and finally we've got 6 electrons for carbon. So the first thing I'm going to do is I'm going to start, as Moseley did, pulling atoms or pulling electrons out and looking for similarities, looking for patterns. So the first thing is to start with hydrogen. So hydrogen has 1 electron total. It has 1 valence electron, and that 1 valence electron is in a 1s orbital, obviously the lowest energy orbital there is. Now Moseley didn't know about orbitals, but still, he did know that there was 1 electron in the outer shell. So he just places hydrogen here. Now helium is a different case because of the fact that helium behaves differently than the elements in this area that we'll have in this area. So we're going to put helium over here for the time being. We're going to leave it there. Lithium has, well, it has 1 valence electron, just like hydrogen does. Has 3 total electrons, so we're going to place lithium directly underneath hydrogen, as Moseley did. Now what we're going to do is we're going to look to see if anything else in our series here has 1 valence electron. I look. Oh, here's one, sodium. Sodium has 1 valence electron, so I place sodium under lithium. Anything else? 2? No? No? Nothing else has 1 valence electron, so I'll move on to 2 valence electrons. So beryllium then has 2 valence electrons, total of 4 valence electrons. I'll put beryllium, as Moseley did, right next to lithium, and then start searching for anything else that may have 2 valence electrons. Well, here we go. Magnesium has 2 valence electrons, so I'll put magnesium directly under beryllium, just like that. Okay, let me scoot these up just a little bit because I think I'm going to need the room here. So that's beryllium. Remember, I've got 18 atoms to distribute. The next one is boron. Boron has 3 valence electrons, and so we'll put this here, total of 5, 3 valence electrons. We'll look for anything else that has 3 valence electrons. I found one, it's aluminum. So aluminum goes right there. And I start to build my periodic table just like Moseley did. The next one is carbon. Carbon has 4 valence electrons, so I'll put that right next to boron and search for any others that have 4 valence electrons. Silicon has 4 valence electrons, put it directly underneath carbon. The next one is nitrogen. Nitrogen has 7 total electrons, 5 of which are valence. I'll put nitrogen there and then look for anything else that has 5 valence electrons. Phosphorus does. I'll put phosphorus directly under nitrogen. The next one is oxygen. Oxygen has a total of 8 electrons, 6 of which are valence. I'll put oxygen next to nitrogen and look for anything else that may have 6 electrons. Here it is. Sulfur has 6 electrons. All right. I'm proceeding pretty nicely here. We have the next one, fluorine. Fluorine has 7 valence electrons, 9 total electrons, 7 of which are outer shell electrons, valence electrons, okay? And now I'll look for anything else that has 7 valence electrons. Found it. Chlorine has 7 valence electrons. I'll put that directly underneath the fluorine. And now what I'm going to do is finish this out with neon here, 10 valence or 10 electrons, 8 of which are valence, followed by argon here. Argon here. I'm going to place helium up here. If I look from left to right, then I can see that I've placed the elements according to atomic number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. That's exactly what Moseley did. And he discovered further that when he looked at characteristics, physical and chemical characteristics, in the columns, otherwise known as families or groups, that things in columns tended to behave similarly. For example, everything in this first column, lithium and sodium especially, are highly reactive with water. Almost explosive, in fact. As you move down the periodic table, if you go all the way down to francium, francium is extremely explosive when placed into water. These are the alkaline metals, this first column. The second column, beryllium, magnesium, and so on, are called the alkaline earth metals. The alkaline earth metals are quite reactive, very reactive. In fact, not quite as reactive as the alkaline metals, but still very reactive. If I go to the other side of the periodic table, neon, argon, and helium, which has only 2 valence electrons, 2 electrons total, those are inert. In other words, they tend not to react with anything else. Right next to them, however, are gases, fluorine and chlorine, gases at room temperature, which are highly reactive. So we see this trend, this periodic trend, as we move from column to column to column. Everything in a column, or a family or group, as it's called, behaves similarly. But what about across a row? What about this way? Well, I'll take a little closer look, for example, at things like electronegativity. Now, electronegativity is the measure of how tightly an atom holds onto its own electrons and pulls electrons from other atoms. If I go from lithium to beryllium, for example, I see 1.4, 1.8 for beryllium, 2.8. It jumps to 3.1 and 3.4, 3.7, 3.8 for fluorine, and neon does not have an electronegativity. None of the noble gases have electronegativities. As I go from left to right, electronegativities increase. Same thing on the second row. If I look at ionization energy, I'm going to go from 520 to 899 to 80 kilojoules per mole, 77. That's 700. That should be 770, 1402, 1314. They're getting bigger and bigger and bigger as I move from left to right across the periodic table. So ionization energy and electronegativity getting larger and larger as I go across the periodic table, with the highest ionization energy being with neon, with neon, and the highest electronegativity being with fluorine, with about a 3.8. So there you have it. Higher electronegativities as I move to the left, higher ionization energy, to the right, higher ionization electronegativities as I move to the right. But what about atomic radius size? Completely different story. If I look at atomic radius size in picometers per picometers, I have 152, 112, 80, 77, 75, 73, 72, 71. Atomic radius size getting smaller as I move from left to right. Same thing on the right-hand side, smaller as I move from left to right. That's atomic radius size. So we've learned a lot from this exercise. So what is your next task? Your next task is to do this. Your next task is to look at the electronegativity, the ionization energy, and the atomic radius size and analyze them. Graph atomic number 1 through 18 versus atomic radius size, then do electronegativity on a separate graph, then do ionization energy on a separate graph, and we'll come back and analyze those results. I'll see you on the next video podcast. Thank you.